So, yay, we've completed particle kinematics. We are still going to do particle kinetics, rigid body kinematics, rigid body kinetics, and vibration. So 20% done. But one of the things that's good to know is that chapter 2 is probably one of the more dense chapters in the entire text. Lots of new ideas, lots of stuff. Chapter 3 is a little bit more straightforward, and hopefully you sort of find it a little bit easier to follow. The quiz, just as a reminder, January 30th, Tuesday, 1 o'clock. Check, make sure that's correct. We're covering everything up to chapter 2.6, which is cylindrical coordinates. Please try and look at geometries and geometry of motion. You will find on the website on Quarkus a whole bunch of old solved quizzes, and if you want to hear my voice explaining gently to you how the quiz is solved, you'll find it also through links. Whoops. All right, so the goal today is kind of to combine chapters 3 and 4. So first, chapter 2, particle kinematics, we have been talking about the geometry of motion. So we haven't told you what caused the force, what caused the motion, but now we're going to look at what does cause the motion. So we're going to look at Newton's 3 laws, free body diagrams, which is going to be a source of great concern for you for the next 2-3 months, and systems of particles. Systems of particles is really chapter 4, but I combined chapter 3 and 4 because they're basically the same. All right. Yeah. Not again. So one of the first things that you guys do, and you did from September to December, was deal with problems where there was no acceleration. And so here, for example, I have a box on a floor, and I have two people that are pressing against the box in opposite senses. Both of them have applied the same force. So it's positive F to the right, negative F to the left, and if I sum them up, I will get 0. And that was Civ 100. So you did bodies, you did beams, and all sorts of things, but basically things didn't move. Okay. That will appear later. Well, what happens if a person pushes against an object that's not with a balanced force? So in this case, the person, the stick figure, is pushing with a force which is going to be F against that block. And the result of that is Newton's second law, which is sum of forces is equal to some proportionality times A. Now, I'm going to avoid this, and I'm not going to spend a lot of time sort of saying what this, magical proportionality is. As far as you're concerned, it's the sum of forces is equal to mass times acceleration. And so that's the proportionality that you end up with. So this is the only equation in this course. Is there a question? So if you take everything we do from this point on, basically chapter 2, just as a reminder, A is chapter 2 and 5, but this is going to be 3, 4, 6, and 3, 4, 6. There we go. That's it. We are only going to look at variations on Newton's second law. So, sort of writing that out finally. Mutual, oh, sorry, that's, yeah, mutual, okay. I'm jumping ahead. If the resultant force is not 0, the particle experiences an acceleration if the resultant force is not 0, the particle experiences an acceleration proportional to the resultant force. So in order for motion to occur, there has to be a force applied, or acceleration to occur. You can have motion. So even though you have a case, say for example, if I push an object on a frictionless surface and I let it go, it will have a velocity that will be determined over, or it will remain constant. If I add a force, friction, or something of that nature, that will play a role in determining what I get from there. And I'm missing one more thing. Okay. So I'm going to put, OneNote is not in a good mood today. There we go. Okay. Oh, there we go. All right, on the other hand, and one of the things that's going to be important, and I didn't have it in here, is if we go back, and it's not in a good mood today. I'm going to reboot soon if I have to. All right. Okay. If I have this case where I have an internal force and I have an object that is experiencing mutual force of action and reaction between two particles. So Newton's third law, and we'll see if we can get through without another reboot, is basically an internal force. And one of the things that's really important, and I will try to fit it in dependent on how my computer decides to act today, is that we have to understand that there are a lot of forces that are acting equal and opposite, and when they do, they sort of disappear from our calculations. But you've got to be careful about how you do that. This is a good time to sort of remind you where we're going. So in the first half of this course, what I have done is look at problems that are based on particles, and they only have mass. However, in the second half of the course, we will be dealing with rigid bodies. And so when you deal with rigid bodies, what the difference is that particles translate. Rigid bodies rotate. And so as they move around, you have to consider the rotation as well as everything else. Okay. The biggest thing you have, and it's not bad when I do it in lecture, it's often surprisingly challenging when you do it at home on your own. You have different problems, but building on the same thing, draw the problem out. And I can see from discussions, from Piazza, from various other sources, it really has to come through that you have to draw the diagram that you're dealing with. And so I do try and draw them when I do the examples, sometimes I think most times. But as you're sort of asking on Piazza, that's another good time to sort of say, okay, here's the diagram that I'm working from to do this. This is not a course on memorization. This is a course on sort of physics with a math bend. Choose your coordinates. We usually give them to you. So that, again, common question, well, when do I choose r theta, nt, x, y? We will tell you usually. And if you look at old quizzes, you'll get examples of that. Define axes, put all the forces on the diagram, and let's consider one straightforward first case. I have a person pushing against the block. And that was the Newton's second law case that I showed you. So the person's pushing against the block is going to have this free body diagram. That diagram is going to be defined with respect to, say, an xy coordinate. It doesn't matter where the xy coordinate is. When I draw it like that, what I'm more concerned about is which terms are positive, which terms are negative. So the normal force here is positive, the weight, mg, is negative, and the force x is positive. So the form of the equations that I'll get is sum of forces x is equal to mass times acceleration x. Sum of forces y are equal to, well, maybe I should do this a little different. Force x equals mass times acceleration x, and n minus mg is equal to 0. So this is really the simplest case. The one that sort of you spend a lot of time on are cases like this, where you have a force that is not applied horizontally, but is applied at an angle. And that angle is theta. And if you start to look at that, you're going to have forces in x. You're going to have forces in y. You're going to have the weight force, and I'll just call it mg, and you'll have the normal force. So sum of forces in the x direction will be F cos theta, because this is theta there, is equal to mass times acceleration x. Sum of forces in y will be n minus mg minus F sine theta, which is equal to 0. Now, it's always equal to 0 unless you have movement in the y direction. And so if you don't have movement in the y direction, I kind of look at that and sort of say, okay, nothing is bouncing. If nothing's bouncing, then there's no change in those cases. We can do the same thing again, where the person is now applying that force, but we also have a friction force. And a friction force is going to be something very common that you deal with, and you'll have force of friction acting on the body, you'll have normals and all the rest. So in that case, you end up with normal, you have mg, you have fx, and you have fy, which make up that f you're given. You finally also have this force of friction, F. I'm not talking, I'll talk later in the lecture about how to define force of friction, but for now we just need to put that in. So it becomes sum of forces in x, F cos theta minus F sub F equals mass times acceleration x. And sum of forces in y, n minus mg minus F sine theta equals to 0. So you're adding in more complexity by having, say, an angle associated with this, by having friction associated with this, and you finally kind of get to the most common sort of case we consider or worry about, which is this one. So I have a box on a ramp, and so if I have a box on a ramp, I will have weight, I have theta, I have defined in the direction of motion my coordinate system. So often when I want to make my life easier, I will define everything so it stays in the, one of the component directions is always in the direction of motion. So here I've twisted it so that it lines up with that theta that I have defined on the ramp. I can also put in a force of friction. Right there. And I end up looking at this. So I have my normal force, which is acting upwards in my coordinate system. However, I have force of friction, which is acting downward, or up the ramp. But I also have that weight force. And the weight force is going to be acting at an angle because of the way I've defined the coordinate system. And that coordinate system, this is again a common case, is then going to be broken up into parts. So I have mgy and mgx. x. So if I do that, and I do the geometry and I put theta in here, I'll end up with some sum of forces x, which is mg sine theta minus force of friction, which equals max, and sum of forces y, which is n minus mg sine theta. And often in these cases, what happens is the force driving the block down the ramp is the weight. And so you're asked for things, all sorts of things like how do you calculate, or what's the acceleration, all sorts of things. And we'll talk again a little bit what this force of friction is. But the important thing is you orient this system so that x is parallel to the direction of motion.
Shouldn't it be close to one also?
Which one? Yeah, it should be close for this one. So we end up with a couple other kind of forces. One of them is spring forces. And we have three different cases we consider: stretched, relaxed, and compressed. And if I have stretched springs, so I take the spring and I stretch it by a distance, so stay consistent, delta x. My force of the spring wants to return to the relaxed state. So it starts here and it will have a force trying to drive it back to this. Now, if I compress the spring by delta x, I'll have a force of the spring, which is like this. And it will try to stretch the spring back into its relaxed position. And so you have to be very careful, but you'll get this equation. Force of the spring is equal to minus kx, k delta x. K is the spring constant. And in this course, it will have units of force over length. And it has, so we just call it spring constant. You'll use K in a couple different things, but K is going to be a standard sort of thing that you reference. Okay, all right, force of the spring. So that's kind of new, but the important point here is this sign right there, that negative kx. Go ahead.
So will the units of delta x tell us the direction of the force?
So the units of delta x will tell us, or well, not the units of delta x, but the direction of x. You're right. So if I compress it by -1 centimeter, then I'll have a negative times a negative, and it's a positive force out. If I stretch it by 1 centimeter, I will have a positive displacement and a negative force associated. So you have to, again, axes matter. Here, we just deal with one dimension. So here's where things get a little messy. We have second law problems that we've started to, but what happens if you have a system of particles? So if I have a system of particles, I can say A, B, and C, A, B, and C, and I'm going to define some sort of control area, control volume, a limit, a boundary. Now, in that boundary, all of the forces are internal, which is Newton's third law. And if they're internal forces, I will have a force of particle A on particle C. I will have an equal, opposite, and collinear force of C on A. So if everything works out for me, and I've done this correctly, all of my internal forces will cancel because force of AC is equal to negative force of CA. So if I add all of the internal forces together in a system, and it's, again, this is not as exciting as it gets in chapter 6, but the important point here is that all of those green, light green forces are going to play a role. So force of AC plus force of CA is equal to 0. Force of BC plus force of CB is equal to 0. Force of AB plus force of BA is also equal to 0. So if I add them all up, they disappear from my expression. So what I'm stuck with are external forces. So the yellow forces, F1, F2, and F3. So when I do the addition, I can say that F1 plus F2 plus F3 is equal to mass A plus mass B plus mass C times acceleration of G. And probably should make those vectors. So if I add all of these external forces together, I have some magical term called G. And G is the center of mass. So if you have a center of mass, that's what you track. So individual particles can displace and do all sorts of things around its center of mass, but the system will have an acceleration in one direction. So you keep following along with all of that, which kind of leads to the question, what is the center of mass and where is it? So if I take that same diagram and I put my coordinate down, I have x and y. I have xg, which is located at ma xa plus mb xb plus mc xc, all over the sum of masses. Yg is equal to ma ya plus mb yb plus mc yc, all over sum of masses. So xa, xb, xc, ya, yb, yc. So it's just a weighted average. So if you have a high mass A and two low mass objects, it will bias towards the high mass object, which kind of makes sense. So the system will depend on, if you have three equally sized ones, three unequally sized ones, you'll have different results. So if you have any two particles any two particles will have a mutually attractive force between them. So here's Saturn and one of its moons, Saturn and Titan. And it can be written, this is Newton suggested. F is equal to G mass 1 mass 2 over r squared. R is the distance between the two objects. Mass 1 and mass 2 clearly are the two different, say, Saturn and Titan. So that's a universal constant, and it has a value, G, of 66.73 times 10 to the minus 12th meters cubed kilogram second squared. And you're really trying to come up with a relationship for the force of attraction between bodies. Now, if you start to think about it, if we're sort of on Earth and we're looking sort of at a quantity like weight, our weight is negligible compared to everything else. And so it's kind of useful to sort of look a little bit at where all of these terms are. So various, nope, okay. So we have G, so mass of the Earth is equal to 5.9742 times 10 to the 24th kilos. Radius of the Earth is equal to 6.378 times 10 to the 6th meters. G is equal to that universal constant, mass of the Earth, over radius of the Earth squared. And no surprise here, it's the gravitational constant. So I have, from that, I'm always sort of calculating that gravitational, or this gravitational attraction between whatever in terms of the bodies. But if I'm on Earth, I just use 9.81 meters per second squared. Now, that would mean sort of different numbers on different places. But I realized I didn't put down the numbers here. But you can see this is Earth. That's Jupiter. You're you'd be, I think this was 100 kilos. That's the moon. And here, the sun. So the same person going from the moon to the Earth to Jupiter to sun will experience different weights. But the mass will always stay constant. So their mass is always the same as they traverse each of these locations. Or if you climb a mountain or you change, so a number of different things can sort of affect you. The important thing out of this, though, is as far as you're concerned, is this. And that you're getting this out of a universal constant. So, go ahead.
When you calculated low case G, why did you only use the 1 mass?
So because what I want to do is eventually use this and say, actually, hold on, let me do this here. Weight equals mg, right? So this is the second mass. So if I have that second mass, then I complete that equation. But I don't have to calculate a crazy number. And that crazy number is 66.73 times 10 to the negative 12th times mass of the Earth, 5.97 times 10 to the 24th, divided by the square of 6.378 times 10 to the 6th. I don't want to do that each time. So I can compress that to this one term. And then it becomes g times m. In the previous chapter, chapter 2, we could do English units. They're not too bad. Lengths are lengths, and things are kind of okay. But when we start to deal with masses and forces, things get a little bit confusing in English and British gravitational units. So mass is in kilograms, and weight is just mass times gravity, and that has units of newtons. And so when I'm looking at a system like this, like an apple, here's an apple that is falling. I have mass of the thing. I have gravity in meters per second squared. And I'll have weight, which is going to be mg in units of newtons. Now, of course, I can switch this to English units, and if I do, I have to be more careful with the units I'm using. Because if I make a mistake, I won't catch it if I don't write those units down. So weight is there. Mass is equal to weight divided by g, which is in units of slug. And weight is in pounds. Yeah, it's just fun. So that sort of leads into here sort of a comparison between the various units. So an SI system is kilograms, meters, seconds, and degrees Kelvin. Yeah. And that has units, or it's a mass, length, time system. British gravitational is pounds force, feet, seconds, and degrees Rankine. And that is a force, length, time system. Finally, you have English engineering. And for English engineering, their pound mass, pounds force, seconds, and degrees Rankine. I will confess, I cannot do calculations in English units or British gravitational units. I don't. If I'm doing calculations, I use them in SI, and then I translate them back into whatever units I'm using. It is important to be familiar with these. It's not, you deal with a lot of customers in the end who expect things to be in inches, pounds, and various other terms. All right. Everyone said it's not right to use English units. Let's use a different system. This is real. This is the Firkin fortnight furlong units, FFF. It's a real unit system, and if you want to check Wikipedia, go ahead. 1 Firkin is 40.823 kilos. 1 fortnight is 2 weeks, so 336 hours. 1 furlong is 201.168 meters. I put it in meters because life is easier. So before I start this problem, I'm going to define a microfortnight. And that's just going to be 1 times 10 to the minus 6 fortnights. And if I do that, I can calculate or convert 9.81 meters per second squared into 1 furlong over 201.168 meters, 1.2096 seconds over 1 microfortnight. And my G is equal to 0.0713 furlongs. Well, that should be squared. I have to check and make sure I actually did this correctly, but I think I did, but I just wrote this wrong. Fortnight squared. This is a ridiculous system. Okay, I understand. But the point is, if you do the unit calculations, everything works out. And if you do the unit calculations, you can always check and make sure that what you have makes sense. You can actually do all of your calculations in this course using this G and convert everything to whatever. But good luck to you. So one thing that is important to sort of make a comment about is why units matter. NASA has very intelligent engineers. Okay, they have really intelligent people who work and know their stuff. And they sent back in 1998, before I think you were born, I know before you were born, this was launched in 1998. It approached Mars September 1999. And then it disappeared. So it crashed into, well, so when it initially happened, people thought the Martians had finally gotten it. We were going to pay for, giant robots were going to come over and kill us all. But what happened was NASA had 2 teams. One working in BG and one working in SI. And this was not communicated. And it was a very high cost loss, because if you're sort of figuring something's happening in feet and it's happening in meters, you're kind of going to be in trouble. And the result of this was that NASA later on changed its documentation procedure to be very, very clear on what units are being used and how those reports are being sent in. So hopefully not another one, but it is kind of an interesting result, because these are highly talented engineers who know their stuff, and that's a terrible, kind of obvious mistake. which would help you, I remind you about the quiz, because it's important on the quiz that you keep your units. Friction. I may have to split this lecture in half. Okay, lots of clever people have measured friction. And basically, this was one of the first cases. And all you need to know is if you rub your hand against a smooth surface, it kind of smoothly goes along. If you go outside onto one of the benches and you kind of try to do the same thing, you'll rip your hand to shreds. And in the process of doing that, you see different coefficients of friction. And so what Coulomb did was he ended up putting sleds with different weights and measuring what the effective motion was under different conditions. This is extraordinarily clever, especially when you kind of realize that this took place in 1773, and doing these kinds of measurements is hard. It's really hard if you have no good clock. Our model of friction is a friction coefficient mu times the normal. So that normal force that we talked about at the beginning of lecture that acts here is how I will extract out what that force of friction is. Now, again, in the course, what we tend to do is give you mu for different cases. So if we have something sliding along, we'll say mu is equal to 0.3, 0.1, point whatever. But what's happening here, the model is this. Oh, I can do this. When two objects slide against each other, so if they're sort of moving, then you have mu sub k. And mu sub k is the coefficient of kinetic friction. Two objects don't slide. Static friction. And that's mu sub s. And we'll talk more about that. Well, we'll talk about it for about 32 seconds, but then we'll continue on Monday. But the important thing here is now I have two things to define what's happening. And that friction, these smooth surfaces that you're dealing with, if you look at them microscopically, are very sort of jagged. And so smoother the surface, the less jagged. But most typical surfaces will have some sort of coefficient of friction associated with motion.